We okay now? You got it now? All right. All right. Any more questions about the homework? All right. Go away. Okay. Time for some math. Time for chapter 5. Time for an actual almost statistic. Anybody here ever heard of a z-score before? Jake? One? Anybody else? High school stats? All right. This is where we're going to take simple arithmetic and apply it to probability theory. Today we're going to do the simple arithmetic. Next class, we're going to throw the probability in there. Because I can tell you what a z-score is. A z-score is just a transformation of our numbers. That's all it is. Right? You can call it standardization if you want. I don't care what you call it. Just don't be scared. So we've looked at this curve before. This is the normal curve. This is our bell curve. It's our normal distribution. What's the area of the bell curve? Okay. Why is it always 1? Because it's a percentage. It's not inches or cubic feet or anything like that. It's always a maximum, a percentage of 1. Right? It represents area, the proportion of the area under the curve. Now, we have talked about this part before. The bottom is known as the x-axis. The one that goes up and down is known as the y-axis. There's actually a z-axis that, if this is x and this is y, z goes like this, which is really hard to do, and you really got to light a candle and have a couple of beers. Because it gets all cloudy, like it rotates and spins. There is also a z-axis. That's 3 dimensions. All right, we're going to stick with 2 flat dimensions. So on our z-axis, what we have here, for example, when we were talking about the empirical rule, we were measuring the area under the curve in terms of the standard deviations. So 68% of our observations are going to be within plus and minus 1 standard deviation. That 68%, 0.68, is the area under the curve. 95% of our values are going to be within 2 standard deviations from the mean. So again, we have the mean. That can be an actual number. We can then also have a separate x-axis, that is the standard deviations. If we wanted to, we could think about this in terms of percentages. The cumulative percentage, if we start at the lowest number at 0%, our halfway point should be 50%. Remember, it's a symmetrical curve, which would leave us with the other 50% on the other side of the curve. All I'm going to do today is introduce the concept of a z-score, which is, here we go, another transformation of the data like we have before. If we start with actual scores and then we go to standard deviations, then we can go to percentages, and now all we're doing is creating a nonsense number called z. Okay. Z, the way it's distributed is to fit the area under the curve. So we're going to start in the middle with a z-score of 0. So z on a normal curve, always, whenever you draw one, this is 0. It's set to have the 50th percentile. It's set to be the most frequent observed number. And as we go out in the positive and a negative direction, we're going to go out to about -4 to +4. Right? We get these, you might have noticed a little bit that the z-score and the empirical rule match up fairly well. That's not by accident. Right? So the midpoint for a z-score is 0. The empirical rule starts at 0 as the standard deviations from the mean in the center. When we go out, our z-score of 1 represents 1 standard deviation from the mean. A z-score of 2, 2 standard deviations from the mean. 3 and 3 and 4 and 4, etc. You got that? Okay. Why do we do this? Well, we want to figure out for all of the distributions that take the shape of a normal curve, is there a way that we can find out the area under the curve from that point? And that's what Z was created to do. So if I tell you that I have a z-score excuse me, one more time. If I tell you that I have a score of X, like Einstein's IQ, where would that fall in the range of all IQ values? Pretty far up there, right? Well, according to this picture I found on the internet, and of course everything on the web is true, let's say Einstein has an IQ of 160. Sure, why not? Where would that place him in the distribution of IQ scores? Well, I do know one thing. I do know that the average IQ score and how they built the test is based upon a 100. So if you've ever taken an IQ test and you've gotten above 100, you are above average. Now, that doesn't mean that you are in the top 50%. It just means you are, again, air quotes, above the average. Whether or not the average IQ score is actually 100, we don't know. But we've been told that that's what it should be by the people who made the IQ test. So let's say you get a score of 160. You're way the hell out here. How different are you from the average person? Well, we can say that you are 60 points higher. But how many people in the world are like that as well? This is where we get into this. Well, it would be really nice to know the area of the curve used up between the mentally inadequate all the way up to the exceptionally gifted. How much of this area is before that point on the curve? How much of it? Any guesses? Okay, 0.9, a lot, but not all, right? I mean, you got to be really, really out here, right? Because this doesn't look like it's very big, right? This section here. Another way of thinking about this is if we start at 1 and we subtract this number here, that tells us how many people are technically above Einstein, right? To the other side of them. So that's why we created z-scores. We created z-scores so that we can compare a value of x with what is the expected distribution of that characteristic, like intelligence. Does that make sense to you? Anybody really freaked out right now? We all good? Okay. So all we're doing is converting our x that we're given to a value in terms of z. That's called the z-score. Okay. So here's an equation for you. Z, the score we're looking for, which is an actual z, it's not a z, we just call it z, is equal to x. X is the value of the observation. So in the previous example, what was x? On my slide from the internet. No. What was x? No. Which was 160. All right, so if we're going to use the Einstein information, Einstein's IQ was 160. Subtract that from the mean. What is the mean IQ score? We think it's 100. We were told it's 100. Divided by the standard deviation. Crap. Because I didn't give you that in the previous slide, did I? Here's the thing. It changes with every data set. 9 times out of 10, when you're given a question on a test or a homework, you're given the standard deviation. Or if they want to be tricky, they give you the variance. Because the variance is what relative to the standard deviation? It's squared, right? So like I said, most times this is just given to you. Stupid internet didn't give me the standard deviation of IQ scores. Let's just Google one and see what Google says. Standard deviation of IQ scores. $15. According to Google talkie person. That doesn't have a name, does it? It's not like Cortana or Siri. Does the Google talking lady have a name? No. Google lady. She who Googles, Google says that the standard deviation of an IQ test is 15. So where is Einstein, his IQ on that z-score chart? Well, let's do the math. 160 minus 100 divided by is, okay, z of Einstein. Four. Way out here. It's so small that giving you the number actually doesn't fit on the chart. What chart are you talking about? Well, don't freak out. Keep eye contact with me. Don't do it. So what have I given you? The standard normal probability. Very good. Oh, I didn't leave it up on the web. Oh, well. Don't worry, I'll edit all this out. Okay. Here we go. Now, I can't write on the screen because it's a PDF, but what do we have here? On the, I guess, your left-hand side, you have a value of z. Okay. Let's start on the one with the positive numbers, 0.0 in the upper. There you go. That's your positive z-scores. So if we get a z-score of 0.00, we know intuitively, just by understanding where z comes from, that what is that point? It's the mean, right? It's the middle. It's the dead set middle of the curve. So when we look on our chart and we go 0.0 on the side and we go over to 0, so again, two figures after the decimal, 0.0 in the row, 0.0 in the column, we get 0.5000. Does that make sense?
I was just pointing out that you're holding that side on the screen.
Oh, dope. Thank you. This is one of those things that because it's symmetric, like in some textbooks, they don't even give you the negative side. They just give you the positive side. Thanks for pointing that out, Tom. Right? So a z-score of 0, 0.0, and then 0 is 0.5. Now, what is 0.5? 0.5 is the shaded area under the curve. So half of the observations are to the, as we're looking at it, our left of the z-score. Does that make sense? Not really. One more time. We have a curve. All of the area under the curve adds up to 1 because it's a proportion, right? The area under the curve in terms of the proportion. The shaded area represents how many observations are under our value. So if we start with a z-score of 0, which when we created z-scores, we meant that to be the midpoint, or whatever the mean is for our distribution, that means that half of it is in the shaded area of the curve, which would mean that it would be this part of the curve. Okay?
So you're saying if you start at 0.0, that 0.5 represents that.
Yeah. Bad curve. We know that when we established a z-score of 0, that this area under the curve so essentially what we've done is we've said you're an average person. Who wants to? Joey. Joey takes the IQ test. Fake Joey takes the IQ test. Joey's average IQ, Joey's personal score is 100. The average score is 100. Google lady tells me that the standard deviation is 15. Joey's z-score is 0 divided by 15, which is 0. I go take that z-score, I look it up in my table, and I know that 0.5% of the, or 0.5 of the population, or 50% of the population, has a IQ score less than Joey. Let's try to look up Einstein. Einstein's z-score was 4. The table doesn't even go that high. All right? The table goes up to 3.49. because you got 3.4 in the column, and then not, or in the rows, the bottom row, and then the 9-digit on the column. So Einstein's way out here with his z-score of 4, which represents a IQ score of 160, right? What percentage is it? Well, the area under the curve for Einstein we know is greater than, and I can never remember which one it is. I always think you point at the littler one. So let's go with that. Is greater than 0.9998. So tenths, hundredths, thousandths, 10,000ths. So if you had 10,000 people surveyed, Einstein would be in the top 2 people. Does that make sense? That's how rare a z-score of 4 is. Okay. Let's do Jake. Jake takes the SAT test. Jake gets an 80. We know the average is 100. We know that standard deviation is 15. We do the math. Negative 20 divided by 15 equals 1.25. That's negative. So let me ask you, for a negative 1.25, how much area does that account for under our curve? So we look on the chart. We turn it over to the other side where the negative numbers are. Negative 1.50. Or sorry, 1.25 gives us an area of 0.1056. What's the area on this side of Jake's score? So how many people, what proportion of the people scored higher than Jake? Hmm? 89.5% of the people who took the IQ test scored higher than Jake. Again, Jake, not our Jake. So what would we say about Jake's intelligence? Enough with the microaggressions. We would say that Jake is educationally IQ challenged and needs additional resources so that he can reach his full potential. Not that you're dumber than, everybody almost. IQ tests are bullshit, by the way. We try to quantify intelligence, but you can't, right? I took an IQ test one time and received a score of 144. Do I look that smart? No. No. I do stupid stuff all the time.
The other thing is they measure it on babies, too.
Exactly. Right? So in 2nd grade, Abby's going to be tested to see if she goes in the gifted and talented program. She's 7. In 2nd grade, she'll be 8. You know why she'll score higher than everybody else? because she's the oldest kid in her class. She missed the school cutoff by 4 days, right? So when she's a senior in high school, she'll be the one that goes out and buys everybody cigarettes because she'll be the first one to be 18 years old. And hopefully it's because she's 18 and not because she has facial hair like her dad did when he was 15 and was the one buying cigarettes for everybody. All right? So she will have an advantage. She will also be the tallest person in her class. She already is. So when it comes time for sports, she's going to be awesome as a senior because she'll be developmentally the same as a college freshman. So there is a reason for some of this stuff and why you can find disparities in things. But IQ tests are horrible. They really are. I am not 144 point smart. It just doesn't work that way. Okay. So this is a z-score. All we're doing is comparing a number that we observe to the mean, right? And again, when I say the mean, I think the mean. Hopefully it's the population mean. It might be our sample mean. And we're accounting for the distance away from the median based upon the amount of spread in our data. Does that make sense? So that's why when we do statistics, we do baby steps. The first part is to understand measures of central tendency so that we can understand what a mean is. The second step is to understand variance or spread, because the variance is what changes the shape of that curve. And now that we have mean and variance, or standard deviation in this equation, we can start comparing individuals and their scores to the mean. Whether it's the mean of the data, so of our 2,306 people that rated Hillary Clinton, we can see where individuals would be relative to the mean. And again, all that depends upon the shape of the curve. So when your last homework talked about skewedness, we kind of want to know whether or not we're dealing with a normal curve or not. But again, for the most part, for reasons that I'll tell you probably next week, we just assume a normal curve. There's this thing called the central limit theorem, also known as the law of large numbers. We'll get to that. But all I want you to do now is to understand what a z-score is. It's a way of recalculating an individual observation relative to the mean and the variance. Does that make sense? Okay. Now, we can do a lot more with this concept of z-scores if we add in probability. So let's think about it this way. If I received 144, I'm just going to round up to 145 for math's sake. My chart does have 3 on it. This area is equal to 0.9987. Still pretty small. It's basically 13 out of 10,000. If we add probability into this, we can then say, what is the probability of somebody scoring greater than a 3? Or less than a 3 in taking the test? Because probability theory, like a proportion, is also bounded between 1 and 0. Remember when we did probability with dice, right? probability of rolling a certain number, 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6, you always top out at 100. Right? You always top out at 1. We're talking about percentages or proportions. So because those two things are the same, we can put this on top of this. So area can not only represent proportions or percentages, but it's also going to represent probability.